Rice University, who will talk about reflectionless canonical systems, almost periodicity, and character-automorphic Fourier transforms. Please, Milivoje.
Thank you very much. Thank you to all the organizers for having me. It's always a pleasure to visit Fields Institute. And today I will tell you about some joint work with Roman Bessonov and with Paley-Wiener. And this work appears split into two archive postings, as you can see. It's broadly speaking, there's a direct and an inverse spectral theory in there. And so really the goal is to the goal is to explain a certain theory of reflectionless canonical systems. And the theory is partly motivated by spectral theory and partly also, but also very firmly rooted in complex analytical methods. In particular, there's a reflectionless property, which is closely related to pseudocontinuation. And Hardy spaces are used as model spaces for certain ergodic, almost periodic operators. And canonical systems and J-contractive analytic matrix functions are at the root of everything that is done. So I'm going to start for motivation with the setting of reflectionless Jacobi matrices. So a half-line Jacobi matrix is one of the most classical spectral objects and can be motivated through orthogonal polynomial recursion or in other ways. Well, but if we have a two-sided Jacobi matrix that acts on L2 of Z, so what makes it a Jacobi matrix is that it has this tridiagonal form. It's a self-adjoint matrix with A ends positive and B ends real. And if we want to understand a half-line Jacobi matrix, we can do so through its correspondence to a canonical spectral measure or through its correspondence to a Weil function. And similarly, if we have a whole line Jacobi matrix like this, you can split it this way, and you get here a Jacobi matrix. So you sort of split it into two half-line Jacobi matrices. You have a J plus here, and you have a J minus there. Both of those are half-line Jacobi matrices. And so J, well, roughly speaking, decomposes into two blocks, but of course not exactly. There's the A naught that couples the two. And but for each of the two half-line Jacobi matrices, you can consider their Weil functions. So this is just this notation may be more trouble than it's worth, right? I mean, it's just supposed to be you take delta 1 J plus minus Z inverse delta 1 for M plus that encodes this half-line Jacobi matrix, and then you have M minus is delta naught J minus minus Z inverse delta naught. So delta 1 is oops, sorry, this is, I don't know what I did here. Okay, sorry about that. Okay, sorry, back to normal. Okay, so you have the, so delta 1 sort of lives here, delta 0 lives here. So this is really the standard canonical way of extracting the Weil function of a half-line operator. And now, of course, a very general famous fact is that this M plus of Z completely encodes this half-line matrix, M minus completely encodes this half-line matrix. So the whole two-sided matrix is encoded by M plus M minus and this coefficient A naught. In particular, this can be used for a lot of things, but in particular, I want to talk about the reflectionless property. So Jacobi matrix is said to be reflectionless on a set E. E is a subset of R. E is think of it as a set of spectral parameters. If the boundary values of M plus and M minus on E are linked this way. So it's a very particular connection between boundary values of two Weil functions, which makes sense, first of all, because these M plus minus are certainly, they're analytic functions, C plus to C plus. They're Herglotz or Nevanlina functions, however you like to call them. And this reflectionless property connects their boundary values. So it's a very strong property, of course, if E is a positive Lebesgue measure set, then this will completely reconstruct M minus from M plus or vice versa. However, it is also a very common property in spectral theory. It's a classical observation that this is true for periodic operators, for example, on the entire spectrum of the periodic operator. And this has been generalized in different ways. Kotani showed that it's a consequence of zero-Lyapunov exponent for ergodic Jacobi matrices, where your ANs and BNs are obtained by sampling some ergodic process. Remling proved in even greater generality that it's a general property of right limits of Jacobi matrices with AC spectrum. So the way a right limit works is you take your if you have a half-line Jacobi matrix, let's say, and if you take its shifts by certain steps, shift it by nk steps, let k go to infinity, see if that converges pointwise in the sense of coefficients, and if it does, what it converges to is called the right limit. And so as long as if the original matrix has AC spectrum, the limit is going to be, the right limit is going to be reflectionless on the same set. So it's really closely related to AC spectrum, closely related to ergodicity and almost periodicity. Now, the reflectionless property from a complex analytic point of view is closely related to something that was well studied in function theory. And so in particular, a function of bounded characteristic on D is just a function that's a ratio of two bounded analytic functions on D. And well, if we have a function of bounded characteristic on D, it's we say that a function on the outside of the disk, on the exterior of the disk, is a pseudocontinuation of F, is if the boundary values match for F from inside and for G from outside. And so this notion is, this is again in itself a strong requirement. So of course, if a pseudo-continuation exists, it's unique, but the question of whether it exists is a subtle question in general. But this is a well-studied property in function theory. And because it replaces, it of course replaces analytic continuation. I mean, because these boundary values are supposed to match almost everywhere. So because it replaces analytic continuation, it allows to generalize a theory of reflectionless operators with finitely many gaps. So there was a theory was developed for a sort of algebra geometric theory motivated partly by integrable systems considerations, where operators are defined on finite gap spectra. One considers operators in finite gap spectra, for example, Schrödinger operators with spectra like this that consist of finitely many bands in a half value and in a half line. So and in those, the reflectionless property is used to extend, to use the two Weyl functions and combine them into a single function on a two-sheeted cover of the complement of the spectrum. And that works well for finite gap spectrum. But if you're interested in something that's more like a Cantor spectrum, this perspective doesn't work. So that's where pseudocontinuation is useful. So one basic observation here is that this can be described using only functions in the disk. So of course, if we just rewrite G using some elementary acrobatics, we can push it to the disk, and then existence of pseudocontinuation exactly corresponds to existence of a function of bounded characteristic in the disk, such that the conjugate of f is f star in the sense of boundary values. So these should again have been limits of f of RT and f star of RT. So, okay, so that's the pseudo-continuation property. And now the question is, if given a compact set E with positive Lebesgue measure, otherwise the reflectionless property is trivial, denote, consider the set of all Jacobi matrices which have spectrum E and they are reflectionless on E. And the question is to describe this set, this isospectral class of reflectionless operators. And one sort of the starting point can be Rachmanov's theorem, which describes that for just an interval, the single interval, -2, 2. For that, the only reflectionless Jacobi matrix is the free Jacobi matrix, consisting only of having only ones off diagonal and zeros on the diagonal. So the more interesting question then is what happens for other sets, multiply connected, and for in particular for sets with infinitely many gaps. To study that, you of course obtain a multiply connected domain, and functions in a multiply connected domain can be studied by using the universal covering. And so in this universal covering, I mean, universal covering is by the disk and quotiented by a fusion group, a discrete subgroup of automorphisms of the disk, where automorphisms of the disk are Möbius transformations of this type. This is really just reformulating what this is stating the standard property, and I'm using J here, but J is just this matrix -1, 0, 0, 1. So this uniformization can be written in terms of the quotient, but also, of course, it's a covering map. That covering map is a meromorphic function, which is surjective. It maps it maps 2 points of the disk to the same point if and only if they are in the same orbit of the fusion group. And also the standard way to normalize this is by normalizing so that 0 maps to infinity. This is, I'm still talking about bounded sets here, bounded E. With bounded sets E and infinity, this is the Riemann sphere, so infinity is included in the domain as an internal point of the domain. And so one way to normalize is to map 0 to infinity, and then the remaining condition is that the behavior at infinity is, there's a remaining argument condition that can be set, and this is how it's set. The behavior at infinity is like C over Z that would C positive. Okay, so with this uniformization map, one can talk about functions of bounded characteristic on omega if they, oh, okay, this is out of turn, right? So if I have a function f on omega, I can pull it to a function on the disk, and then we can talk about bounded functions of bounded characteristic in omega if their lifts are of bounded characteristic in the disk, and so on. Similar for a Hardy space. But of course, we've in doing this and in applying complex function theory, we quickly step out of this setting. In that, for example, in an inner-outer factorization, even if f is single valued, its inner and outer parts in general are not. Only the absolute value of f will be single valued, but they might differ by a phase. And so what happens is that this very quickly gets you from a setting of an analytic or meromorphic function on omega to the setting of multi-valued functions on omega with a single valued absolute f. And such functions, of course, if you follow an analytic if you follow this multi-valued function along a certain path, if you follow it along a certain path in the multi-valued sense, you're going to pick up a phase, and that phase will be something unimodular. So for every gamma, there's a phase alpha of gamma, so that this is true, where f composed with gamma denotes just an analytic continuation of a multi-valued function along a closed curve. Now, this, of course, is, again, this is more precisely written. Instead of thinking about multi-valued functions, it's more precise to talk about their single-valued lifts to the disk. And in terms of the lifts, we can write this basically in the same way, but now f composed with gamma denotes composition of functions. So now big F is a function on the disk, gamma is an automorphism of the disk. So this really just denotes normal composition of functions. And yeah, so these are, of course, two complementary points of view. This can be more intuitive to us because omega is the original resolvent set, and greater interest this way. But of course, the lift has advantages. Okay, so if we're in this setting, now clearly, if you compose this or this picture for more than one closed curve or more than one automorphism of the disk, you get this. And so alpha is an additive function. So it's an additive map from gamma to r divided by z. And the function f is said to be character-automorphic with character alpha. So, okay, so this group of additive maps like this is called the character group. And this motivates defining for any character alpha, defining the Hardy space of functions which are the Hardy space of functions which are in the Hardy space H2 of D, but are also character-automorphic with character alpha. So the character group gamma is fixed here, and this should more precisely be big F. Big F itself is what lives in the disk. So, okay, so this is well defined, but the question is it non-trivial? And this was studied by Widom. So for a Dirichlet regular domain omega, we say that it's of Widom type if there are several characterizations. There are characterization in terms of green functions and so on. But the most direct property that is useful here is that it's of Widom type if and only if these character-automorphic Hardy spaces are non-trivial for all alpha. So for every character alpha, this is non-trivial, and that's the regime in which we want to work. So this is of course true if it's a finite gap set. So everything I say here generalizes a finite gap setting, but it's also true more general. Now, if you have this, as soon as this is non-trivial, it's a reproducing kernel Hilbert space. It's a reproducing kernel Hilbert space because H2 of D, the Hardy space H2 of D, is a reproducing kernel Hilbert space, and this inherits that structure. So for every point in the disk, there is a reproducing kernel such that this holds. And these reproducing kernels take a role where they can be used to construct for the functions with certain properties. Now, the Dirac-Cauchy theorem, so there's a further property that is useful here, and it's called the Dirac-Cauchy theorem property, but it's a property that holds for some Widom sets and fails for others. So it's kind of confusingly named theorem, but it's a property. So this DCT property is said to hold for omega if and only if the reproducing kernel is continuous. And so this is another setting that is useful, and you will see how continuity is very useful for what we do, is necessary for what we do. So one remark, just as ways of example, is that if you take a standard Cantor set construction with, well, not the middle third construction, but a version in which you get a positive Lebesgue measure Cantor set, then that is a Widom set with the DCT property. So this is a class of examples where everything we say applies. Okay, so a certain breakthrough in this work was done by Sodin-Yuditskii, who in this setting considered exactly this isospectral class of operators that, remember, this is defined as the set of operators which are the set of Jacobi matrices which have spectrum E and are reflectionless on E. And Sodin-Yuditskii proved that that all reflection that this is equal, that this is equivalent to the Jacobi matrix being almost periodic and having spectrum and a absolutely continuous spectrum equal to E. And moreover, Sodin-Yuditskii provide an explicit parametric description of this isospectral torus. So there's an explicit construction of certain two-sided Jacobi matrices, let's denote them J of alpha, parametrized by a character alpha, such that this gives the entire isospectral set. And now, of course, gamma, remember, I mean, gamma star just consists of additive maps from gamma to R minus Z. So one thing I should have said right away is that this character group is a torus, right? It's a torus of dimension equal to the number of open gaps in the spectrum. So for what is our main interest, the infinite gap situation, this is an infinite dimensional torus that parametrizes. And so it's in fact very common to call this kind of isospectral class, to call it an isospectral torus. In certain situations, this is known to be like here, and in others, this is not as well understood. But okay, so in this case, certainly it's an isospectral torus. It's parametrized by a torus in a continuous way. Now, one of the ways to read this set of results is that reflectionlessness here implies almost periodicity. Remember, this is opposite from what you get from Kotani and Remling, where ergodicity, almost periodicity, right limits give you reflectionlessness. Here, reflectionlessness implies almost periodicity, and that follows by this kind of explicit construction that provides all two-sided Jacobi matrices with the right spectrum. Now, I should remind here that so what do I actually mean by a Jacobi matrix is almost periodic? So for a sequence, for a bounded sequence, we say that it's almost periodic if the family of its shifts. So you take the sequence B and you shift it to the left or to the right. That gives you a bounded set in L infinity, in little L infinity of Z, and that bounded set may or may not be precompact. Well, if it's precompact, that's exactly when we say that B is an almost periodic sequence. Right? So this is an almost periodic sequence. Another equivalent characterization, and the way you often obtain almost periodic sequences, is by a continuous sampling. And so this will now seem immediately relevant given what I said here. If you have a continuous sampling function on a torus, and you have a starting point, and you have a direction vector, and you have a continuous sampling function, and you sample it linearly going along that torus. That is an almost periodic sequence. So these are in fact equivalences, and so this is stated for a sequence. But then we also say that J is almost periodic if the sequence of ANs and BNs are almost periodic sequences. So J has this tridiagonal form, and it goes this way. Okay, so for this parametric description, one key idea is, so in the Sodin-Yuditskii perspective, the Jacobi coefficients really are obtained from some continuous sampling functions kind of in this form. Now, that sampling, the n that comes there, comes with a certain nested family of subspaces. So there's a point of view, for example, by Nikolsky of using Hardy spaces as model spaces for ergodic and almost periodic operators in his treatise on the shift operator. And the way that happens for Jacobi matrices is as follows. If you remember, infinity has a special role for a Jacobi matrix. And remember, the uniformization map maps 0 to infinity. And so let's look at the orbit of the pre-image of infinity, or the orbit of 0, and take a Blaschke product corresponding to that orbit. And of course, if you want a 0 at infinity, you have to take a 0 at all points of gamma, at all points of this orbit. So you get a Blaschke product. And in this Blaschke product is non-trivial, it's convergent, and it has character, it's a character-automorphic function with a certain character beta phi, which I'm just going to denote by beta here. So one basic observation in this setting is that factoring a 0. So if you want to take your space H2 of alpha, and if you want to factor it, if you want to decompose it, sorry, I don't mean factor. If you want to decompose it as a direct sum of things, you can consider the subspace of things that are 0 at 0. So if you look at the subspace of things that are 0 at 0, you can, of course, factor out that 0. And when you factor out the 0, you factor it by factoring the Blaschke product. Everything's in a character-automorphic setting. So one factors out the Blaschke product and obtains, but the Blaschke product has a character. So factoring that gives you an arbitrary H2 function, but with the changed character. And so iterating this gives you a family from H2 of alpha, a family of nested subspaces, which shrinks to 0 as n goes to infinity, and which on the other side goes to just L2. And so this nested family of subspaces corresponds to our it's a nested family indexed by n and z that corresponds to the two-sided Jacobi matrices, and also corresponds to their truncations from n to infinity. So the question is then, and this is where I get to something newer, is what happens if you have if you want to, instead of a Jacobi matrix, if you're interested in a continuous analog, in something like something differential instead of a difference equation, or from a complex analytic perspective, what happens if E is an unbounded spectrum? So important work by Marchenko-Ostrovsky, they considered periodic Schrödinger operators, characterized that, isospectral torus, a lot of things there. A question that was posed by Crane-Levin was to develop this theory for Crane strings to have much more general half-bounded spectra. But a lot of things change profoundly when you're interested in an unbounded spectrum. In an unbounded spectrum, infinity is no longer an internal point. There's a certain Akieser-Levin dichotomy with respect to how, so infinity becomes a boundary point. So if you have a set E subset of R that's unbounded, now you're interested in the domain that's C minus E, and infinity is a boundary point. And then the question is, what kind of boundary point it is. So there's a dichotomy there, and there's complications. You don't have, for example, this complex green function. You don't have a Blaschke. You don't have the same object. So, okay. Moreover, having unbounded spectrum, because it goes hand in hand with having a continuous model, you expect that this should correspond to a continuous family of subspaces, which should correspond to restrictions on an interval x to infinity. And there have been, of course, previous works for specific classes of operators, for almost periodic Schrödinger operators. And those works are based on finite gap approximation and trace formulas. So one uses the finite gap construction and uses trace formulas to produce convergence of these finite gap approximations to an almost periodic object. So these are not truly functional models natively in an infinite gap situation. And in particular, in order to push through a finite gap approximation, say if you have finite gap Schrödinger operators and you want to push that to an infinite gap situation, it requires you to have it requires a certain gap summability conditions, and it doesn't tell us anything about the function theory and of what happens if what happens without some kind of gap summability. Okay, so in particular, two questions that I would single out here is, if you have an unbounded Widom set with a DCT property, without assuming anything else, what kind of almost periodic system corresponds to that? What kind of almost periodic system correspond to this spectrum, to this as a what kind of reflectionless almost periodic system? And also, in what sense are they almost periodic? You saw the Jacobi matrices are uniformly almost periodic. Now, our work gives a general construction of reflectionless canonical systems in R of gauge, and I will define what that means. And the data of in these canonical systems are almost periodic measures. So this answers these questions. The right setting in which you always get almost periodic systems is the setting of canonical systems in R of gauge, which I will define, and almost periodicity. The notion of almost periodicity you have is of certain almost periodic measures. Now, I should define another ingredient here, which is the Martin function. So I'm working, as I've said plenty of times, unbounded subset of R. And I need to define the symmetric Martin function to infinity. So this is a positive harmonic function on omega, which has this symmetry. I'm always working with Denjoy domains. E is a subset of R. And the Martin function is going to have, we're interested in the symmetric Martin function, which has this symmetry. And also, we're assuming Dirichlet regularity. So the Martin function vanishes continuously on E. The symmetric Martin function is uniquely determined by this up to normalization, up to a rescaling factor. It extends to a subharmonic function on C. So its distributional Laplacian is what we call the Martin measure. Okay, the Martin measure is mutually absolutely continuous with Lebesgue measure. And the Martin measure, the Martin function is a positive harmonic function, right? So since it's a positive harmonic function, so let's view it as an imaginary part of an analytic function. If you view it this way, then you will have an analytic function on omega, but this analytic function on omega is not single valued. Only its imaginary part is single valued. So this complex Martin function theta has the property that, well, if you take its analytic continuation along some closed loop, that this boosts by an additive character. Notice that now this additive character is not in the exponent. It's just, it's an additive shift by a real constant because the imaginary part is single valued. So, of course, again, this eta as a function of gamma is additive. And notice that one thing that happens is because now eta is just a real valued object, notice that now you are allowed to take a continuous family of inner functions with, well, I'm precise here, but with some Hardy spaces of this form. So once again, there will be some kind of linear shift in character and a factorization of some inner factor. But now L is continuous, and this is okay, right? These functions are character-automorphic in the sense discussed previously, and L is now a real parameter. Okay, so I should, another motivation that I like to point out is that our work provides certain eigenfunction expansions for these reflectionless objects. And those eigenfunction expansions are really just character-automorphic Fourier transforms. And so what we get is character-automorphic Fourier transforms which behave in some way, which act as character-automorphic versions for the following. If you consider the standard Hardy space on the half plane, defined of course by this norm, then the Paley-Wiener theorem describes exactly with the standard Fourier transform what subspace corresponds to that Hardy space. So Hardy space can of course be seen as a subset of L2 of R, and that is precisely the subset that maps to L2 of 0 infinity. More generally, of course, from that you could get a map of these subspaces e to the ILZ to L2 of L infinity, and you should notice in this something that's going to be replaced by something that looks like this, and here by some kind of map L2 of L infinity. So that's this nested family. And so we construct Fourier character-automorphic Fourier transforms, which are unitary. I'll try to show that. Okay, so let me now let me start saying the results. So one direction is that almost periodic implies reflectionless. I've already mentioned Kotani and Remling, and if I want to work in the canonical system in R of gauge, it wasn't proved before in this setting, but it's but Remling's theorem is very robust, and so for a canonical system in R of gauge, what we call really an initial value problem like this. So we write it in integral form. So so A of ZL are 2x2 matrices, and so of course these are integral from 0 to L. So this is just saying A of Z0 is identity, and then you have it's just an integral version of an initial value problem, just an integral formulation, which involves a measure mu on R. The measure mu is continuous. It may not be absolutely continuous. We'll see, in fact, that there's a natural parametrization that comes for us that's not always absolutely continuous. But so for a measure mu on R and a function like this from R to the closed unit disk, this is a canonical system in R of gauge. J is just a signature matrix. And so we prove that if the coefficients here are almost periodic functions, if the coefficients are almost periodic in the sense that the measure mu has a certain almost periodicity for every step size t. If you evaluate mu on a window of length t, you look at that as a function of the starting point, that's almost periodic. And a similar thing for the complex measure a d mu, integrated over step of size t, taken as a function of the starting point. Both of those, if both of those are almost periodic in L for all t positive, then, excuse me, then the canonical system in R of gauge is reflectionless. So that's the direction from almost periodicity to reflectionlessness. What about the opposite direction? Well, if you have as I said, a Dirichlet regular Widom set with DCT and unbounded, then all reflectionless canonical systems in R of gauge with spectrum E are parametrized by they're parameterized by character group, and there's an extra parameter, there's an extra degree of freedom that's an extra circle. Don't mind that. But again, so we have a way of constructing explicit parameters, mu alpha and here A alpha, so that these give us all the reflectionless canonical systems in R of gauge. And the explicit parametrizations here allow us to see that these are almost periodic measures. Namely, for any piecewise continuous compactly supported test function, if you integrate this is a version of what I've written on the previous slide. You integrate with respect to some test function, and and you slide you look at how it behaves under translation, you get something almost periodic. Okay, the parametrization in canonical systems, one can usually reparameterize by, it's an initial value problem, right? And if you reparameterize your independent variable, it changes the system. But our canonical systems are parameterized so that the solution obeys this natural growth rate. And that's like it's like a certain exponential type, but with respect to the Martin function. So okay, so that's the direction from reflectionless to almost periodic. Now, this R of gauge might look strange or exotic, but the triumph here is that it always gives you an almost periodic system. This is not true for other settings. And so, for example, canonical systems are often studied in what we call the Potapov-de-Branch gauge. Some people will call them just the branch canonical systems. And in Potapov-de-Branch gauge, you write a canonical system in this form. Notice that here there's a z in front. So really, this form is the previous form was more like az plus b, with a and b of a certain type. This form is just like a hz. So in particular, systems like this are normalized at 0. And whereas canonical systems in R of gauge are normalized at I. This was not very clear from the formula I wrote, but this is the way the normalization goes. And because the Potapov-de-Branch gauge, they're normalized at 0, you see that because you see that at z equal to 0, nothing happens here, right? So at z equal to 0, you see that b of 0L is just identity, just because, I mean, there's nothing here. This vanishes. So, okay, so we show that this doesn't always give almost periodic data. And the problem is precisely that these are normalized at 0, and 0 could be, and 0 is in general not an interior point of the domain, and there's boundary effects that mess this up. However, so if you have a point, so if 0 happens to not be in E, then there's no problems. But if 0 is in E, and if you additionally impose a certain Lebesgue condition near 0 and a certain harmonic measure condition near 0, then your reflectionless canonical systems in Potapov-de-Branch gauge have an almost periodic matrix measure. So one of the ways to view this is that we have a general almost periodicity result in R of gauge, and that can then be specialized under suitable additional condition, can be specialized to other settings. And another one that I want to point out here is Dirac operators. So Dirac operators in their 2x2 form are a very related equation. The transfer matrices for Dirac operators obey a Dirac equation like this, where Q is you could call it the potential, which satisfies this, and well, so it's a transfer matrix equation for the Dirac operator, and if you have your properties of E as before, and in addition you assume gap summability, then your reflectionless Dirac operators are parametrized by, again, by the same kind of enhanced character group, and they have uniformly almost periodic potential skew. And this is done by taking the canonical systems in R of gauge and transforming them using this condition, transforming them using certain normalizations at infinity, which are required for the Dirac setting. But infinity is again a boundary point of the domain, And so that's why additional conditions are needed. So I only have a minute, so I'm going to, here I was going to tell you something general about these J-monotonic families and how canonical systems relate. I'm actually just going to tell you, I'm going to tell you something else. I'm going to tell you just what is this based on. For a character alpha, if you, what are the model spaces? I wrote down some H2, but those were not the same H2 as before. So in the unbounded case, we need to take Hardy spaces with respect to Martin measure. And so it's the set of Smirnov class functions F with norm given by integrating along E the boundary conditions with respect to Martin measure. If you were taking this with harmonic measure, you would get the usual Hardy space. Okay, but once again, these character-automorphic Hardy spaces embed into an L2 space, and they are non-trivial reproducing kernel. Hilbert spaces, so they have their own reproducing kernels, K alpha, and that K alpha in particular taking certain values at I allows you to construct construct certain measures. And so that looks like this. Now, this doesn't look very appealing, but well, the point is that this defines two measures. One can then prove that the second measure, so the first measure is positive, the second is complex, and it's of this form. And these are these parameters that I promised that would be almost periodic parameters. And you can see in this a certain almost periodicity, a certain linear motion with character in all these formulas. So that's all I'd like you to take away from that. Okay, so finally, there's some Fourier transforms that are character-automorphic that are given explicitly in terms of all these objects. But I'm gonna stop there. All I want you to see how everything moves with the character. And so, okay, so that's it. Thank you. Thank you very much.
Thank you, Milivoje, for a wonderful talk. Let's thank Milivoje. Questions, comments, suggestions? Okay, if there are no questions, let's thank Milivoje again. And we have about 7 minutes before the next talk.